I got 2 out of 3. So remember, this sign, it doesn't matter because you can easily flip the sign. But remember, in Dr. Sama notes, she put minus here. If you want to apply the formula from the notes, follow the same notation. Is that okay? So far so good? So right now you see, we use the next estimation to build on the right now estimation, but multiply by plus something here. This is my learning rate. That's the reason why I call L, learning rate. Agree? So right now, what's the observer? Observe the error here. So remember, we define the error is xt minus xkt, right? But is this error observable to you? No. If this is observable to you, you can access this one. Then you can actually know the state. Then estimate here it doesn't make any sense, right? If you know this one, you can get this one. Then estimate this one doesn't make any sense. So what's the estimate like observe the error you can observe? Is this one y minus y hat. This is the error you can observe, right? You use the truly output minus your estimate output. This is the error you can observe. Question?
What's the output?
Y?
So y is also being outputted there?
Y hat is my estimate output. So that's the reason why you need this one. So far so good? So basically this term, why Dr. Sama's note we put y minus y hat here. It's because that's the only error you can estimate, you can observe. If you can observe this one, then you can just directly observe this one. Then there's no point to estimate the whole thing. So the issue is we use the output error multiplied by this learning rate to make sure this one eventually converge.
Would you give us the learning rate, or like how would we?
You need to design your learning rate.
We just.
Yeah, so later on we need to determine how to design an L. But I want to explain to you more intuitively about why it makes sense. Because you use an arrow multiplied by the learning rate, and you add it to here, you wish this eventually converge to this one, right? So you wish eventually the whole term here goes to 0. If you wish this one goes to here. So far so good? So the only issue is like y here will be minus L times y minus y hat. We have a very, very long history, like a story behind it. This is the only error you can observe. And it's 1 by 1 scalar. So that's the reason why your L, right now here, your L is 2 by 1 vector. So far so good? That's the reason why your L is 2 by 1 vector. Remember original we say, I think I already erased it, sorry. Original we say you need 2 points to find like your estimation for your 2 states. But since right now you only observe 1, right? So you just assume this one works for both states. So that's the reason why you have a 2 by 1 learning rate. 1 for each state. Does it make sense? Agree or not agree? Great. So remember, during exam or homework, double check if this is minus or plus. If it is minus, you can follow Dr. Sama's note and apply the formula. If it is not, if the form is different, learn how to derive it. Is okay? So right now, if this is true, we have the whole things. Then the next story is which L to make this one converge to 0. Is okay? So which E of t equals to x minus x hat goes to 0. Okay? So E of t equals to x. I just plug in the whole formula here. So you have a times x plus bu. For x hat, I just plug into the formula I write down here. I just built this model. It's okay? This formula is given, but it's given by some logics I explained to you. So in minus, the whole thing is a x hat plus bu minus L and y minus y hat.
Is the error the difference of the derivatives?
What?
Is it the difference of the derivatives?
Oh, yes. Oh, we wish this one directly goes to 0, right? So, if it goes to 0, derivative goes to 0, you find this one, you got the whole thing here. So, right now, let's just do some calculation. I think we need to plug in y here. Y is ax. Oh no, y is cx. And this one is cx hat. So that's good. And plus bu minus bu, we cancel these two terms. So that's good. So what left is a times x minus a x hat minus times minus, we got a plus here. L multiplied by cx minus cx hat. So that's good. So eventually we have a x minus x hat plus LC x minus x hat. So eventually you have a plus LC x minus x hat. This equals to, oh my gosh, I'm so tired too. So this equals to a times plus LC arrow. So that's good. So you see, the first derivative of your arrow, you got a plus LC times an arrow.
You're telling me this isn't a formula, we can just basically copy that.
If your model is like this,
Trying to do this on model?
and double check this is minus.
Yeah, how many points in that question? Oh, it's only 20.
If we did the wrong model, but we did everything correctly, like
0 point, of course. Kidding. Kidding. We will try our best kind part, very generous part to grade your exam. Okay, so right now you wish the arrow converge to 0. You wish the whole matrix here, A plus LC, the eigenvalue for this one is what? It's converged, right? So if it's discrete time, then you wish like the eigenvalue less than y. If it's continuous time, you wish the eigenvalue real part is less than 0. So that's good. So you see, right now, if you build out this estimation, you can find out your arrow multiplied by the matrix here equals to your arrow derivative, the first derivative. Right? Okay. So if you wish if you wish, eventually your x hat converge to x. Of course, you wish this term eigenvalue fulfill this requirement, then you know the eigenvalue, the arrow here converge to 0 eventually. Does it make sense? So remember, even though I derive for the discrete continuous time, but you can still derive for the discrete time too. Question?
Why did you make it so it's like E dot?
Yeah. Remember, eventually we wish this one goes to 0. Right? But I have the formula is x dot and x hat dot. So I want to apply those two formulas. So I put dot, dot, dot. Does it make sense?
Yeah. But why does having the like A plus LC have?
So if you put this one, I derive LC, I find out x E dot equals to the matrix times this one. Right? In which this term goes to 0, then this matrix fulfills this requirement.
Isn't that like a constant matrix though? Like isn't it not to change?
This is constant matrix?
No, the like A plus LC.
Right now I want to design my L. You see, when I told you the whole story, I only told you this formula makes sense. But I didn't told you what kind of L you need. I only told you how many L you need. You need 2 by 1 vector here. But what's the number for your L? Your learning rate. I haven't talked about it yet, right? So right now, we find out it should make the matrix here fulfill this requirement, and then you can make sure your arrow converges to 0. Then your estimation eventually goes to x. Does it make sense right now?
Oh, so you designed L to make your height values follow that.
Yes.
Oh, okay.
Let's repeat again. We want to build an estimator, estimate x hat. So we already discussed the logics here, right? We agree with this one. But we haven't talked about what's the L we need, right? And we want to design the L, make sure the x hat eventually converges to x, right? Question?
L is just a 2 by 1 vector that we can like choose.
Yes. So right now, we only told you build on this formula makes sense, but we haven't talked about what kind of arrow we want. So right now, the value of L should be determined by this matrix fulfill this requirement. Because if you know you define this arrow goes to 0, converges to 0, you wish the whole eigenvalue for this matrix fulfill this requirement. Is that okay? Does it make sense? So you just like the first thing we discussed about how the logic write down this formula. The second thing is like let's find out the value L. The value L should make the matrix, the whole matrix here, fulfill this requirement. Then you will say your estimator works. The x hat eventually converges to x.
Yeah.
So there's going to be a lot of values of L that will work. You pick any one that makes it happen.
Yes!
Okay.
Yeah! Woo! Finally we agree on this. So far so good? So we already agree with the whole thing, right?
Wait, are we done?
No, of course not. I want to talk a little bit more about this matrix. This matrix eigenvalue tells you how fast your arrow converges, right? So if I told you I wish my arrow converge like a c exponential minus t plus c2 exponential minus 2t. Oh, actually, I should write down like this. c1 exponential minus t, c2 exponential minus 2t. I wish the arrow converge like this. It means like the eigenvalue, the first eigenvalue for this matrix should be 1. Right? Should be minus 1, should be the here. So if we give you the term here, you should know the eigenvalue Is okay? Should be -1 and -2. Agree?
Wait, what is that? Oh, you did it.
Yeah, because I just told you like this term, this matrix times E is a 2 by 1 vector, right? So I wish this one times the E equals to its derivative. So basically, the eigenvalue determine your convergence rate here, right? So if you wish these two fulfill some rate, basically we partially already talked about the lambda you need. It's okay? If you only want to talk about does it converge, you got multiple lambda. You got the lambda is not unique. You got a range. But sometimes we can define the convergence rate for your arrow. You should use the convergence rate to determine the eigenvalue. You can check the past final exams. We have this type of functions. Okay.
Is the x hat not given?
X hat dot given? Yes. Yes. If we don't give you, then you should ask during exams. Okay, so we already agreed. We already agreed how we design an estimator, right? Question?
Are we going to derive this? Can we just say a plus LC?
This is a really great question. If we during exam we give you exactly same formula, no, you don't need to derive it. You just plug in the formula. But if we give you different one, then that's different story. Then you should tell me different result, right?
Are you making the test or is Summer
Can you tell her to give us this one? Make sure
No, she already gave us this one. We're chilling, yeah, we're good.
Okay. So I don't care about the exam. My job here is to make sure you understand the whole thing here. Learn how to derive it.
She's pretty nice.
She's pretty. Okay, so let's go to the second story. So assume we already built the estimator correctly. So the x hat right now is perfectly fine. So we can see, let's assume the whole thing here. The whole thing here is just my systems. Then we back to state feedback control. Right? If you already built a beautiful, nice estimator here, then you assume the whole system here is your system. Then you just back to your state feedback control. Right? So find the state feedback control closed loop for this one. You need one more thing. There's a little bit difference. It's between this and the state feedback control we just learned. It's like, this is the second order system. You have two states. How many states you need for this one?
2.
You also need 2, right? But how you define your state? Do you want to use x hat? Okay. If you, right now I want to use state feedback control. You look back, and you only multiply, this is 2 by 1, right? And you look back, you want to design a system here. But how many states you have right now? You have 2 from H. Actually, you have 2 from E2. But if you're using x hat, if you define your new state like this, it's really redundant. It's really redundancy because eventually this converges to this one, right? So in Dr. Sama note, we define the new state is E here.
Wait, what's that?
So right now the state for the whole system I just circle here is you put x is 2 by 1 vector and E here. Instead of using x hat, you use E. You use this one. This backward here. Does it make sense? Because if you use x hat, you know eventually x hat equals to x. You just write x twice.
So this is for the state feedback control with the SM.
Yes. So if we going to define the state for the whole system like this, you find out the new state like this. So you have a dot here. So you will equals to xe plus something multiplied by your input R. So you see, for the closed loop, we need to find out, even though k is 1 by 2 vector, but you have 4 steps. You have 4 steps. The first two from H, the second two from your estimator. And you follow the whole derivation, you know it will be a plus bk here minus bk, 0, a plus lc, b, 0. I know I'm jumping a little bit fast, but let me tell you what's going on here. We know E dot, we know the second part, E dot equals to a plus lc times E, right? We just derive here. Okay? We know the whole story, this one. So far so good? So the question part is like what's going on top? The first row. Is okay? So go back here. You notice here will be k times x hat. So this summing point, again, is our good friend. So u equals to r plus k x hat. So we plug in the whole thing here, back to our state space model. But remember, we don't want x hat anymore, because I don't define my x hat as my state. I define E as my state. So when you plug in, replace, eventually I want to replace this U to my state, Xe and R, right? So if you got R, this is what we want, but we don't want X hat, because we just say we don't define X hat as our state. We define E. But remember, E equals to X minus X hat. So X hat equals to X minus E. So you have, so far so good? So right now, that's the reason why for this one, when I introduce the K, we depend on X and R right now. So the rest story is we plug in what U equals to this one back to this formula. So we got X dot equals to A times X plus B multiplied by R plus K times X minus E. So we got AX plus BKX minus BKE plus BR. So these two we can combine together. We call it like A plus BKX. That's my term here. This one times your X. Minus BK times E. So this is B minus BK times E. And plus BR. Plus BR. Okay? So right now, because you define your state is arrow, your new state is X and then arrow. So you need to replace X hat as X minus E. Is okay? This is how we learn like a closed loop state space model. Oh, my camera guy, are you leaving? Okay. Okay, so that's the reason why we replaced the whole thing here, we're back here, so we got this beautiful matrix. And for the closed loop, this is my closed loop matrix right now, right? And since we already make sure this one eigenvalue fulfill we want. Fulfill should require. Is okay? When you want to feel the estimator is correctly estimate your result eventually, you know the eigenvalue for this one should follow the requirement, should fulfill the requirement. But the whole eigenvalue for this one, your eigenvalue for your ACLO is your eigenvalue for your A plus BK union. This is your union of your eigenvalue A plus LC. It's okay? So you see, this give you 2 eigenvalues. This will give you another 2 eigenvalues. It's okay? So eventually we give you 4 eigenvalues. So if you want to use state feedback control with observer, output feedback control with observer, the first thing is make sure the eigenvalue for this one less than 0 or like real power less than 0, absolute power less than 1. If it's discrete time or continuous time separately. The second story is like you also need to design your K control again to make the eigenvalue to anywhere you want as you designed before. It's okay? So that's the whole story for output feedback control with observer. The first thing is you should know the formula here. Makes sense. The second thing is you should know the arrow, how the arrow goes to 0. The requirement is here. The third story is like you consider the estimator and the system into together as like a whole systems. You find the new state. It's okay? Define your new state. The third story is like once you define your the first like a new state, you find a closed loop for your whole systems. And then you will notice like the eigenvalue, 2 of the eigenvalue from your A plus LC, 2 of the eigenvalue from your A plus BK. You design your L to make sure the estimator works. You design your K to make sure the whole matrix to fulfill the region you want, the requirement you want. Then that's the end of the class for this part. And sorry, I don't think I have the time to go through the final exam. I will release the solutions on Blackboard. So double check it because I know you guys are too tired. And thank you guys for letting me tutor like a TA for you this year. I'm very grateful and very fun to teach you guys. I know it's really overwhelming today, but thank you very much for the whole semester. I will stay longer if you have any questions you can ask. Thank you. Yeah, because eventually you want this system to go to something you want. That's assume the overall system will be those things. Then you want to make sure all the eigenvalues fulfill something fine. So you will be given more requirements to design. Okay. So it's just more like if you already know the whole story and then know how to write it. Sometimes we will give you the convergence rate. Sometimes we'll give you the property we want. We want to make sure the whole matrix is exactly stable. Then you need to know how to find the range for K and L. Yeah, so this is how we learn before.
Yeah, so like, it doesn't go back much past this inflection and the problems like on applying stuff.
I couldn't tell you, but you should learn the whole formula and learn how to derive it and make sure you understand each of us.
Yeah, I just want to be able to do practice stuff in terms of finding what L is and finding. You said like maybe like certain eigenvalues like stable.
Yeah. We have
the problems that would happen.
From the past meeting. So I will release the solution.
Okay.
Sorry, it's too late.
Oh no, it's fine. Thank you. Thanks so much for semester too.
Is he releasing or releasing?
Yeah.
Thanks, Jinbu. Especially for the cookies. Okay. If it's continuous time, you only care about the real part. Because the sigma help you to convergence. Imaginary part is just like a frequency. So we care about it. So for discrete time, you wish the absolute value less than 1. No, absolute value is not real part. Absolute value is the radius. Like how they usually call the radius. Is that okay? So let's assume one part is A plus IB. If it's continuous, you only care about A. If it is discrete, you compute A squared plus B squared, A squared plus B squared, and the square root of the whole thing.